Now, students, as we discuss the properties of the diamagnetic material, if you remember, I was telling you all in the last class that the materials which, when placed in a magnetic field, acquire feeble magnetism in a direction opposite to that of the field. So this, if you look into this diagram, well, if you have a field which is generated between two pole pieces of two magnets, north and south pole, directed in this manner, and if you have a diamagnetic material here, within the diamagnetic material the magnetic field will move from north to south, but outside the material it will be from south to north. So here the field acquired is in a direction opposite to the direction of the field. Okay, so inert gases, a majority of metals and many organic compounds are diamagnetic substances. Now hydrogen, air, water, gold, silver, bismuth, as I told you yesterday, are examples. And well, the salient features we were discussing yesterday, they are the follows. As I said already, that diamagnetic materials exhibit negative susceptibility. Diamagnetic materials exhibit negative susceptibility. Okay, and well, as I said just now, the direction is opposite to the direction of the applied field, and we have seen also yesterday that this is of the order of 10 to the power minus 6. Okay, next we discussed that the since the diamagnetic susceptibility is negative, the relative permeability mu r is actually slightly less than unity. It is less than 1. Mu r is less than 1, and well, these substances are repelled by magnetic fields. So if we draw the diagram over here again, from north pole to south pole, again we have the magnetic lines of force like this. They are moving in a specific direction. Alright, and you have a diamagnetic material, alright, like this, from south and north. Then well, you will see in this case that the magnetic lines of force, they are sort of repelled, while it likes, it's like this, it goes like this, kind of repulsion takes place. So you will see a kind of magnetic field lines moving away from one another. So this repulsion is observed in a diamagnetic material. Alright, now if we place a diamagnetic material in an inhomogeneous magnetic field, it tends to be pushed into the regions of weaker field. So when the material is taken, say in the form of a small rod, and if we freely suspend the material, okay, in the magnetic field, it turns to a position perpendicular to the field lines. Okay, which again means that diamagnetic materials, well, diamagnetic materials, okay, push aside the field lines. They push aside the field lines. Alright, so the next observation that we make of the diamagnetic material is that the diamagnetic susceptibility is independent. This I had discussed with you all, that the diamagnetic susceptibility is independent of temperature. it is independent of temperature. Okay, this we had discussed, alright, and this was experimentally verified by Pierre Curie. So Pierre Curie experimentally verified that the diamagnetic susceptibility is independent of temperature. Alright, so number 5, what was the observation? We have seen that the magnetization M is a linear function of the magnetic field H when the magnetic field is not too strong for a diamagnetic material. So M is a linear function of H for a diamagnetic material. Okay, is that okay? All right, so these were what we had discussed already yesterday. Now the thing is, let us find out certain properties of paramagnetic material, because these are to some extent weakly magnetized or non-magnetized. So what properties do we see of paramagnetic materials? Let us find out. Well, the paramagnetic materials are substances which, when placed in a magnetic field, acquire feeble magnetism in the direction of the magnetic field. So, acquires feeble magnetism in the direction of the magnetic field. Acquires feeble magnetism in the direction of the magnetic field. Alright, now what are these typical examples of paramagnetic materials? Oxygen, solutions of iron salts, copper chloride, chromium and platinum are examples of paramagnetic materials. Now what are the salient features? So oxygen, okay, chromium, platinum, solutions of iron salts, copper chloride. Okay, so solutions of iron salt, copper chloride are some of the examples of paramagnetic materials. Is that okay? Alright, now you see what are the salient features. So let us discuss the salient features of paramagnetic materials. Salient features of paramagnetic materials. So what are the salient features? Well, you will see that a paramagnetic material exhibits positive magnetic susceptibility as the magnetization coincides in direction with the magnetic field H. So chi M is positive. Okay, the reason is that the magnetization coincides, the magnetization M is in the direction of the field. M is in the direction of the field. Is that okay? So that is the first salient feature that we are talking of. right now. Okay, the other salient features are, well, the relative permeability mu r. So number 2, the relative permeability mu r. Mu r is actually uh, slightly more than unity. It was slightly less than unity for paramagnetic. So mu r is slightly more than unity for a diamagnetic material. For a paramagnetic material, not for a diamagnetic, for a paramagnetic material. Okay, so here the field lines are pulled towards the material. So here you will see the picture goes like this, like what we had drawn previously for diamagnetic material. Okay, here the picture is the following. You see, this is your north pole, this is your south pole. Okay, and here you have your, say, paramagnetic material. Okay, so where this is south and this is north, so as the field lines move in this direction like this, you have field lines moving in this direction, then here within the material the field lines are from south to north in this direction, but outside the material it is from north to south in this direction. So here also, if it is from south to north in this direction, outside the material it is from north to south, it is in this direction. Okay, so here what do we observe? In this case, suppose say we have here the north pole, here we have the south pole, and here you have your paramagnetic material, then the field lines are pushed inside, unlike the diamagnetic material. Here you will see that the field lines are pushed inside like this. Is it alright? So the field lines, rather it's like this, it's like this. Okay, so it's like this, it's like this, it's like pushed inside, the field lines goes inside. So this happens in a paramagnetic material. Alright, so what is the feature number 3 that we observe? Number 3, the feature number 3, what is it? Well, when a rod of paramagnetic material is freely suspended in a magnetic field, it aligns itself along the lines of induction. Okay, so a paramagnetic rod aligns itself in the line of induction. A paramagnetic rod aligns itself in the line of induction. So in a non-uniform field, the paramagnetic substances are attracted towards the stronger region of a magnetic field. If a paramagnetic liquid, if you take a paramagnetic liquid in a U-tube, for example, you have, say, a U-tube like this. Filled up with paramagnetic liquid. So this liquid is a paramagnetic liquid. Okay, so and if you keep it between the pole pieces of an electromagnet, suppose say this is your north pole and suppose say this is your south pole, so you keep it between the pole pieces of electromagnet, the level of the liquid rises in one end. So you will see the level of the liquid rising in one end and the level of the liquid in the other end comes down. So this happens for a paramagnetic material, because the paramagnetic substances are attracted towards the stronger region of the magnetic field. Alright, salient feature number 4. What is the salient feature number 4? Well, here the magnetization M is a linear function of the magnetic field, same as diamagnetic, is linear to H when H is not too strong. And this feature number 5, well, the paramagnetic susceptibility is strongly dependent, it is strongly dependent on temperature. So chi M is strongly dependent on temperature. It is strongly dependent on temperature. Okay, all right. And chi M is strongly dependent on temperature, and well, this was again discovered by Pierre Curie, and the dependence has been studied in the form of chi para is equal to C by T, where C is a constant, and this is called Curie law because it was discovered by Pierre Curie. Okay, so this is called Curie law, and C is Curie constant. C is the Curie constant. Now the temperature dependence of a paramagnetic susceptibility is, you can see it in the 1 by chi para plot, which is plotted as a function of temperature. So if you just look into this plot, this is the plot. So you see this is 1 by chi para. This is susceptibility chi of paramagnetic material. When you plot it against temperature, you will see that this plot goes in this manner. So this shows that 1 by chi para well increases with temperature. Alright, and this thing holds up to a sufficiently high temperature. A departure is observed in case of solid and liquid paramagnetic substances at low temperature. At very low temperature you might see a departure, and that's why I have put dotted line over here. Okay, but at high temperature this is pretty well followed. Okay, now the behavior of chi para in this case was described by Curie and Weiss, chi para, through Curie-Weiss law. The Curie-Weiss law says that chi para is equal to C by T minus theta. I'm just discussing the salient features because you do not have the proofs of all these, but these are really very important and they are considered as the salient features. So the behavior of chi para is given by this law, which is called, Curie-Weiss Curie-Weiss law. Okay, all right. So well, so here this is called the theta p. This is called theta p, where theta p is the paramagnetic Curie point. So how do we define the parameters? C is the Curie constant, theta p is the paramagnetic paramagnetic 20 points. Okay, and this C and theta P, they are actually C and theta P are different for different material. Okay, all right. So we'll do a problem on this, on paramagnetic material. What is it? The susceptibility of paramagnetic, the susceptibility of paramagnetic Fe2Cl3. So let me write chi para instead of writing susceptibility. The chi para of FeCl3 is 3.7 into 10 to the power minus 3 at 27 degrees centigrade. What is obtain mu r at 200 degrees Kelvin and 500 degrees Kelvin. So if you just go by chi para is equal to C by T, if you just go by this, chi para is equal to C by T, then C is equal to chi para T, isn't it? So you can find the value for C. Then from there you can find the value for chi 200 Kelvin and chi 500 Kelvin. Just do it and give me the result. Okay, all right. Now next